Look at a neural network. Ask, when does the network begin to strongly associate a pattern in the input with a corresponding pattern in its output? And what is a pattern? Imagine we're biologists making measurement in the field. Each dimension of our input vector could describe some property of a plant. Petal symmetry, leaf roughness, stem thickness, membrane temperature, so on. We can assign each property a number. Maybe 0 means almost no petal symmetry, and maybe 1 means perfect symmetry. Our input vector is no longer just a meaningless list of numbers. Each dimension has an interpretation. And we can do something similar to the output. Maybe each output cell corresponds to a plant category: daisy, marigold, orchid, sunflower, and so on. Now, the interesting relationship do not necessarily live in individual dimensions. A certain combination of dimensions, say high petal symmetry, moderate smooth leaves, and a particular soil condition, might repeatedly be associated with a certain combination on the output side. And in other words, some linear combination of input dimension can be associated with some linear combination of output dimensions. And I'll call one such relationship an input-output mode. And remember the word mode, it'll show up again. This video, we focus on the simplest form of neural network, 3 numerical layers. In it, the strength of one of these associations can remain weak for a long period, rise rapidly over a relative short interval, and then saturate near its final value. If that mode happens to correspond to something interpretable like in a biologist's example, it can appear as if the network has suddenly acquired a new concept, which is often layers of abstraction above the interpretation assigned to dimensions. Maybe it's a high-level biological categorization. So why does this rapid transition happen? And what determines when it happens? And mathematically, how can we even measure how strongly a network has learned one particular relationship in the data? I'll sit back as we dive in. First, I want to formally reintroduce you to our network. We multiply x by W21 to produce the hidden layer h, and then multiply h through W32 to produce the predicted output y hat, which would in turn equals W32 W21x. More, we have true output y coming from the real data set. So y hat usually does not match y initially because both matrices start essentially untrained. Their difference gives us an error vector. And the first lecture in machine learning would ask, how should we change the numerical values inside W21 and W32 so that y hat gets closer to y? And take the top left self W32. This particular weight multiplies one particular hidden layer value, which comes from a row column multiplication from x and W21, and that product contributes to one particular output value. As the highlight shows, these are all associated. So if the output number is wrong, changing that selected weight can push it upward or downward. And in the most extreme case, we could simply set every other weight in the output row to 0. Then choose this one weight to be exactly whatever number makes its age multiplied to the correct target. And do the same thing for the next output row, then the next one, and eventually we could construct a matrix that gives essentially 0 error for this one input-output pair. Sounds great. But the instant we replace x and y with another data point, we're cooked. A real data set does not contain one observation. The biologist might make samples from all around the world, so their data set might contain hundreds, thousands, or millions of input-output pairs. A matrix handcrafted to exactly satisfy one pair has no reason to satisfy all the others. We want to change that minimize the error across the whole data set. Let's go back to one selected weight. How much should we change it? Well, remember that this weight multiplies a particular hidden layer value. If that hidden layer is large, then even a modest weight contributes strongly to the output. But if the hidden layer is small, well, changing the same weight has a much smaller effect. So the update should depend on the magnitude of the corresponding hidden value. Now, it should also depend on the output error. If the output is already nearly correct, the correction should be small, but if it's badly wrong, the correction should be larger. I'll put those together. For an individual weight, the update has a basic structure, error times h. There should also be a global step size constant, call it lambda, which determines how far we actually want to move in that update direction. So the basic idea is not nearly as frightening as the final equation we have. It's just update is proportional to error times h. Well, now each cell in W32 is uniquely associated with a cell in the error vector and a component in the hidden vector. Well, that immediately suggests a compact operation. Take their outer product. The error vector is a column, h transpose is a row. Well, then error times h transpose produces a matrix with exactly the same shape as W32. Every cell in that new matrix contains one error component multiplied by one hidden component. It's the exact local relationship we just derived cell by cell. So instead of separately saying, this weight gets hidden 3 times error 2, this weight gets error 1 times hidden 5, the entire matrix update can be written all at once. Since error equals y minus W32 W21x and h equals W21x, but we're using its transpose, the update equation becomes this. This complicated looking expression fundamentally still says error times h. We can derive the update for W21 in the same spirit, but I won't spend another 5 minutes deriving it. The important thing is that both matrices now have mathematically defined update direction. But remember, we have many training examples, so we repeat this update calculation for every input-output pair and add their contributions together. We can make notation much cleaner by placing all the individual input vectors beside one another as columns of a matrix. So matrix X is simply x1, x2, all the way through xm placed side by side. And we do the same for y hat, h, and y. This starts to look intimidating, but nothing profound happened. Each column is still just one ordinary training example. Now, if we bring x transpose into the bracket, two strange-looking matrix combinations appear: y times x transpose and x times x transpose. Well, at the first sight, this is much less intuitive than treating the formula as error times h. So why would we deliberately rewrite the equation this way? Because these matrices expose structure in the dataset itself. But first, let's call y-x transpose sigma 3 1, the input-output correlation matrix. Well, each cell in sigma 3 1 combines one output dimension with one input dimension across the dataset. Go back to our plant example. Now, suppose the input cell means petal symmetry and the output cell means daisy. One large value in the corresponding part of sigma 3 1 means that across the dataset, large petal symmetry values tend to occur together with large values on the daisy output dimension. It is not literally a conditional probability table. It is a numerical measure of how strongly those two dimensions co-vary across the dataset. And because we compute this for every input dimension against every output dimension, the entire matrix records a giant web of input-output relationships. A digit classifier gives us a more visual example. Imagine converting every handwritten digit image into a long input vector, one dimension for every pixel, and have the output vector contain 10 dimensions, one for each digit from 0 to 9. If a particular cluster of pixels tends to light up strongly in the image of 1 and 4, then the corresponding entries in the input-output correlation matrix will become large for the output dimensions, representing 1 and 4. So the matrix begins to contain visible structure. Which regions of the input tend to accompany which output categories. And this gets us close to the question we started with. If we want to know when a network learns a pattern in the data, we first need some mathematical description of what patterns are present in the data. And sigma 3,1 is where those input-output relationships live. But there's another matrix in our update, XX transpose, which let's call sigma 1,1. This one compares input dimension with other input dimensions. Using our plant examples again, maybe petal symmetry and leaf roughness tends to vary together. Maybe leaf roughness leads to more petal symmetry for some biological reason. Then sigma 1,1 records that relationship. And that creates an annoying problem, because we're trying to understand how strongly petal symmetry and leaf roughness together predict some plants like daisy. But petal symmetry and leaf roughness are already correlated in the input data. Then the input-output relationships we observe are entangled with relationships that are already existent inside the inputs. Let's choose whitened input. This means we're working a basis where sigma 1,1 equals the identity matrix, erasing itself from our equation. And this means, in the more technical term, that the input dimensions have unisecond moment and zero cross-correlation, which I don't know what they mean, but do know that orthogonal input vectors satisfy that condition. And under this setup, sigma 3,1 is exactly the matrix we want W32 times W21 to approach, because in equilibrium, changes are zero, and that's only possible if this term is zero. Pause and ponder, because we're going next step. Ask, what hidden structures exist inside this target matrix? And one thing we can do is to decompose it into its what I call natural modes. Suppose I vary one ordinary Cartesian input coordinate. Well, several output coordinates may change at once. Then I vary another input coordinate. Again, several output dimensions change, but these two output change directions may overlap strongly in the sense that their dot product aren't zero. So input dimensions are orthogonal, but their output under the network generally are not. In our ordinary coordinate, multiple input-output relationships remain mixed together. What we really like are special input directions whose corresponding output directions are also orthogonal. So might there be a linear algebra manipulation tool that makes this possible? Yes, we can diagonalize, because diagonalizing a matrix is like diagnosing a matrix. It sort of diagnoses the eigenvectors whom are special co-orthogonal directions that, when multiplied with the matrix, gets mapped back onto themselves, only changing their magnitude. But sigma 3,1 might not be a square, so instead we use diagonalization's brother method, singular value decomposition, which decomposes sigma 3,1 into U33 times S times V11 transpose. Each row in V, let's give it an index alpha, describes a special direction that, should we send it through sigma 3,1, gets S alpha, which are the singular values we refer to in the method's name, times U alpha. More importantly, these U alpha directions are mutually orthogonal. First, this is diagonalization in spirit, because it also maps orthogonal input to orthogonal output, just not in the literal input's direction. More, this is exactly what we wanted. Special input directions whose corresponding output directions are also orthogonal. To proceed, we can order these singular values from strongest to weakest from top to bottom, which means also reordering the corresponding singular vector pairs in U and V. This is perfectly allowed because each row and column are just sort of eigenvectors. Their order doesn't matter. Now, Look at the SVD. Sigma 31 originally looked like a random pile of numbers. Now they've been reorganized into independent input-output modes. And each modes are a trail of row, column, and diagonal S cell. And they're independent because they're all co-orthogonal. Each mode says this input pattern maps to this output patterns with strength or magnitude S alpha. Whether a mode has a nice human interpretation depends on the data set. Maybe one loosely corresponds to a biological distinction, maybe it doesn't. The mathematics itself only gives us a structured direction. Now, remember that our network is trying to make W32 times W21 approach Sigma 31. So it makes sense to express the network weights in the same singular value coordinate. We rotate the input side by V, rotate the output side by U, define transformed weight matrices, and rewrite the learning equations in these mode coordinates. The algebra becomes much cleaner and something extremely interesting appears. For a particular mode, alpha, take the corresponding transformed column from one weight matrix and transform the row from the other. Their dot product measures how strongly the current network maps the input mode V alpha onto its corresponding output mode U alpha. The target value of this dot product, which is the value the dot product should eventually approach as training finishes, is the dataset's singular strength, S alpha. And I'm gonna tell you forefront that how close is this dot product to S alpha is the answer to our original question of how strongly has the network learned one particular input-output relationship. And before I tell you why, if you like this video, subscribe. I'll make more content like this in the future. Now, let's get back. Why? Look into the transformed equations. We get two kinds of terms. The first is the same mode term. It directly contains S alpha minus A alpha dot B alpha. And those S alpha terms are not zero. But for the term to be zero, which reminder is required in the equilibrium, A alpha dot B alpha of the same index approaches the strength for that mode. But we also get cross mode terms, things like A alpha dot B beta, not on the diagonal, beta not equal to alpha, indexes not the same, no correspondence. At equilibrium, zero, the cross mode term disappear. But remind you, S is diagonal, which means these non-diagonal term is already zero, which means the sum of A alpha dot B beta is zero. Notice how it's different from A alpha dot B alpha, who goes to S instead of zero. So, recap. Matching mode approaches their target strength. Mismatched mode becomes orthogonal. This is what I call a decoupled regime. And back to what we care about, remember? How close is the dot product A alpha dot B alpha to S alpha? Well, if we simulate the full coupled system from a generic small initialization, the dot product against time looks like this. Slow initial development, a rapid rise, then saturation. This looks like a sigmoid curve, is it? Can we derive a clean exact formula? Yes, but it's extremely annoying right now. Every mode not only has to make its dot product with the same index term go to S, but has to make sure all the dot product summed goes to zero. There's just too much things to care about. So we make our lives easier again. Define an orthonormal hidden layer basis R. For every task mode, constrain the corresponding transformed row and column pair to lie along one shared hidden direction, R alpha. Different mode gets different orthogonal R alpha directions. Then, from the very beginning, R alpha transpose times R beta equals 0. And therefore, all those cross-mode dot products vanish. We can rewrite the equation in differential form and focus on the individual node instead of the entire matrix. So the matrix equation reduced to a simple scalar differential equation, which, when solved, plotted, become exactly what our simulation shows. When the dot product is tiny, the update is slow, but at some crucial stage, as if some supernatural force is involved, the dot product rises rapidly. But as the dot product approaches its target S alpha, the learning slows again. And since different modes can have different singular strength and different initial condition, they can enter the rapid learning window at different times. Even though on the surface, loss boringly decrease, hidden there exists a sneaky window of time where the update of weights of the connecting matrices starts to demonstrate strong pattern association in the dataset. If one of those modes happens to correspond to something we recognize, perhaps some interpretable feature distinction, it may look as though the network has suddenly understood something. Real neural networks are much messier, and modes may not map cleanly onto concepts, but the lesson remains. Learning can uncover them on different timescales, sometimes gradually, sometimes in sudden stages. Just like in real life, when you struggle on something for a long period, you feel like you're not progressing forward. But just might that you suddenly enlightens and go through a qualitative change of how you approach the problem. Neural network can learn in stages, and sometimes so do we.